Is it raining outside?
It is.
Yeah, again. Winter is finally here and it's supposed to be almost spring. Oh, well.
Surprisingly, winter in California, spring California, but
Yeah, I guess so. Yeah,
winter feels more like spring.
a month from now, we should finally get spring coming.
At the longest, yeah, the first half, that's right. Yeah, since then I have a bit every single week.
For the key. Winter next week. And then next for the. Constantly winning them like. I'd rather say like once.
Hey guys, hello and welcome. I think I'm gonna go ahead and get started here. It's nice to see all of you today. It's nice and warm in here, which is nice. I know it's been kind of chilly, rough weather, and I'm getting ready to go somewhere very cold. So I am going to be going on that trip. I think I mentioned I was on the fence about it the other day. It was kind of depending on the weather. And it's kind of on the edge, I have to be honest with you. I contacted my partner. It's supposed to be 30-mile-an-hour wind on the summit on Saturday. That's a little bit right on the edge of what I would be good with, but he's like, yes, we should do this. So I'm like, all right, I'll come. So anyway, I am going to do that, and it's going to not affect us very much because I'm not going to miss any class. We're obviously here now. We're going to be here again next Tuesday. But in the meantime, I am going to the airport tomorrow morning early, and I will be kind of out of off the grid, let's say, tomorrow and Saturday. If everything goes according to plan, however, I should be done with everything by Sunday. I'm not coming back here, however, until Tuesday morning, because when I made my plans, I was like, well, let's give ourselves the best window of time we can, and that was as much time as I could do. So I'll be staying up with my friend, but I will be able to be online on Sunday and on Monday. So the way I'm going to do the office hours here, I'll be around after class tonight for sure. But then tomorrow I sometimes have those Friday hours. We're not going to do that. So no hours tomorrow, but I will do Sunday and Monday. These will be only in Zoom. So be sure to come to the Zoom office hours. In the evening, either night. Definitely on Monday, I'm cutting it off at 11. I've got to get to the airport very early Tuesday morning to fly back here in time for my classes on Tuesday. So, but anyway, that is what's coming up. And in order to make this work as well as I can for our homework assignments, there was supposed to be an assignment due on Friday night. I've now moved that to Sunday, just so that if you do have questions, you can come talk to me during my Zoom office hours. That's totally okay. If you already have some questions, you can throw them on the board over here during our break today, and I'll try to maybe peek at those a little bit. I have to be honest, we've been going a little slow through the homework. I gave you a whole week to do assignment 9, almost a whole other week for 10, and now here we are. A few days later, and that's fine. It's nobody's fault, really. It's just the way the timing has gone. But just as a heads up, there's going to be a increase in the homework because we are going to get through all of the first 14 assignments before we have another midterm, which is 2 weeks from today, actually. So to help us out with this, here's the way I'm going to do this, and I hope this won't be too confusing. I've got a video that I've already sent out to you guys to watch before class on Tuesday. I must have it before class. This is critical that you do it before class, otherwise you won't understand what we're doing in class on Tuesday. So be sure to watch it before class. You'll get 4 points of extra credit towards your second midterm if you just take the notes on that and scan it in before class on Tuesday. I think it's a 70-minute video, something like that, a little over an hour. But don't just take the notes, try to understand it, try to learn it, obviously, because that's what we're going to need to know. But that extra credit video is about chapter 5. And today we're actually going to finish chapter 4 in half the class or less. And instead of starting chapter 5, I'd rather let you watch that video first. I think it would be more efficient to do that. So what I'm actually going to do is jump ahead today and start covering chapter 6. For your next midterm, the first section of chapter 6 will be on that midterm. And so I figure I can, and the 2 chapters don't have to go in any particular order. So I'm going to jump ahead to chapter 6, which is why you see me jumping from homework 11 to homework 14. I don't want to renumber the homeworks. Homeworks 12 and 13 are based on chapter 5, which we're going to come back to. I actually think chapter 5 is a little bit easier. We'll come back to that one. And so what I'm going to ask you to do is, in addition to this video before class next Tuesday, I would like you to do homework number 14 by next Tuesday as well. It is only one section, 6.1. And we are going to talk about chapter 6 today in class here. So I'm hoping I'll get through most of what you need for this homework. If there's anything next Tuesday, by the way, in case you're wondering, we are actually ahead of schedule. So it's not, that's not the issue. So it's just that I'm leaving town, and so it's just creating a little bit of a problem with the timing of it. So, but my point being that if I don't get everything covered that you need for homework number 14, I am planning next Tuesday to spend plenty of time in class to go over any of those problems. So just do the best you can to get as much of it done before you come in here next Tuesday. I'll obviously answer questions, and we may spend more time than normal going over homework questions because they're good practice problems. Might as well just use those as practice. So anyway, how does that sound to everybody? Is that gonna be okay? You'll survive without me for 2 days? If I don't make it to my Zoom office hours on Sunday night, something probably very wrong. Don't worry, I'll have a contact with, I always take a Garmin with me so I can send a message out. Come save us, bring the helicopter. I gotta get to my office hours. So anyway, I think it'll be okay. This mountain is not that high. It's just that it's kind of a rough time of year to go do it, but my buddy wants to do it. So anyway. It's not supposed to have any precipitation this weekend. I mean, the mountain is a snow white volcano. It's all white. It's had snow all winter, but they're not supposed to have anything currently coming down while I'm on the mountain, which is very important. If that was happening, I would cancel. But it's supposed to be dry this weekend. Yeah, so I have to take crampons, ice axe, all that stuff. I'll take some pictures. I'll try to show you some pictures next time. Yeah. Hopefully there'll be some pictures to show. Anyway, yeah, so that's the game plan for the next few days. Let's see, I have a recap kind of in 2 places here. The one that's on the screen over there, you don't need to write that down. This one here is just the table that I had produced for you guys on Tuesday. If I have a set of vectors, let's say I have k vectors in a set, I'm calling the set S here. If I have k vectors and I'm working in a vector space whose dimension I know, remember the dimension is just how many vectors for a basis. The number of vectors in a basis, that's called the dimension of V. So I can compare how many vectors they gave me with what I know the dimension of V to be. And I've reminded you of some of the very important dimensions numbers that you should know down here. Everybody should know these cold. The dimension of Rn is n. The dimension of the m by n matrices is m times n, and so on. Polynomials, n plus 1, and n by n matrices would just be n squared. So these are dimensions that we already know ahead of time. And on Tuesday, I wrote down bases pretty much for all of these to give you some examples of them. And so if we know the dimension of our vector space and somebody gives us k vectors from that vector space, I can try to decide whether they are, well, linearly independent, whether they're going to be a spanning set, or in the case of both, that would be a basis. Remember, a basis is just a set that's both Li and spans V. So could be both or could be neither. And what you see here is depending on how the K compares with the dimension of V, we can rule out 2 of the 4 wrong answers immediately, right? So if I give you K vectors, and if K is too many vectors, if K is bigger than the dimension of V, then there's no way that they could be Li. And so then, of course, they're not going to be both either. If I don't give you enough vectors, it's the other way around. Then I know that the vectors don't span V, and obviously they can't be both, right? if I give you the correct number of vectors, then those vectors are either both or neither. And you might remember from Tuesday, when you lay the vectors into the columns of the matrix, in this third case over here, that matrix will be a square size. Because the K matches with the dimension of V. And if it's a square size, you can take its determinant. So I put a little note here. You've got a question, is it both or is it neither? And the answer is it means yes on both, as long as the determinant is not zero. Okay. If the determinant is zero, then this one's no, and then this one's yes. So obviously it's one or the other. But you see a few question marks in this chart. That's because, yeah, if I give you too many vectors, well, I don't know. Maybe they span the space, maybe not. We'd have to actually put them into the columns of a matrix and augment that matrix with those hashtag number symbols and just see whether the system is consistent. We'd have to actually just do the work, the EROs, to sort of see where the pivots would end up. So anyway, I kind of like this little table. Notice the bottom row. Neither is always on the table. It is always possible, no matter what I give you, whether it's too many vectors, not enough vectors, or the right number of vectors, neither is always one of the two options that could be the case. Angel?
And the question was relating to 4.6.
Okay.
So this idea also applies if you gave us like matrices as the vectors,
Mhm.
like you gave us K matrices, all this applies to that.
I think there's a homework problem where I gave you 6 matrices that are all 2 by 3.
Yeah.
Right? So the matrices are 2 by 3. So this is one of the homework problems for assignment 11. I gave you 6 2 by 3 matrices. Now the universe of 2 by 3 matrices is 6-dimensional. So it was the right number of vectors. So in that case, you are over here in the third column, and it's yes or no. Now, you could put those matrices into the columns of a matrix, which would create a 6 by 6 matrix. I don't really want to take the determinant of a 6 by 6 matrix if I can help it. There's something on that particular problem that I know which one you're talking about. There's something about that list of vectors. If you look at it closely, you can see what the answer is supposed to be without having to actually take the determinant.
Yeah.
Without giving you the specific problem, I can't give you much more of a hint than that.
But yeah, in general, like the matrices count as a vectors.
If I'm in the vector space of Mn of R or M by N of R, then my vectors are the matrices, right? We still have this matrix that we are setting up with columns filled with those vectors. But that big matrix is just the tool that we're using to sort of analyze this whole problem here, right? As opposed to the actual vectors themselves, right? The 2 by 3 matrices in this case themselves, which are coming from that vector space. Yeah, so matrices can be vectors. That is certainly one of our very commonly used vector spaces. Good point. Any other comments or questions about this little summary over here? You'll have to let me know what you think of this. I've never put this up before. I've taught this class 30 times. I've never made this table so that people could see the yes, no, the question marks and all that and kind of how that lays out. I would love to know if you think that's kind of helpful.
Yeah.
Is so far so good. I also have this thing over here. Now you don't need to take notes on this one. Before I actually talk about it, let me just show you where it is. In Canvas, if we close this for just a second, there is a, where is it here? Here's files. There is a folder that's called special handouts. And somewhere along the line, I made a handout. It's called Recap for 4.6, 4.8, and 4.9, which is exactly what we're going over right now. And that is this document that I just talked to you about. So this handout has a reminder about what a basis is. Okay, so it's Li and it spans V. The number of vectors in the basis, that's N, that's the dimension of V. So we learned all of this on Tuesday. And then here's my notes. If K is bigger than N, if K is less than N, I really shouldn't use an N here. I should just write dimension of V, I think would be better. But comparing the K with the dimension of V, we find out that the vectors, they cannot be Li or they cannot span V. Or they're both or neither, right? This whole text right here is really summarized by that table. So if you like the table format of it better, you can certainly use that. But yeah, so just another place in the Canvas page where I have that summarized. And then the bottom half of this handout, this is actually what I wanted to talk more about right now. This is a summary of what I was doing towards the last part of our class on Tuesday. We did a lot on Tuesday, right? So I was talking about fixing a matrix and that there were 3 important subspaces associated with that matrix. And I used to come in here and put this all up as my recap, and it just took too long to write it down. So I made it into a handout so we don't have to recopy all of this. But what it has is, first of all, the 3 subspaces. So we talked about the null space, the row space, and I sort of talked about the column space. I'm going to say a little bit more about it in a moment. These 3 subspaces, what are they? So the description of them. So null space, a set of solutions to AX equals 0, right? Row space, that's just the span of the rows. The column space is just going to be the span of the columns. And these are all subspaces. They're all subspaces. And I always like to remind people that we should tell ourselves what they are subspaces of. And it all has to do with the M and the N, of course. And so the null space, well, you can see from the description that the X's are in Rn. Right, so the null space is a subspace of Rn. And then, by the way, there's also a column for the dimension. The dimension of each of these is just, well, for the null space, it's just called the nullity of A. So we talked about this on Tuesday. It's just a word. If I want to know what is the dimension of the null space of a matrix, I'm really asking for the nullity of that matrix, right? And it's actually just the number of free variables that you get in the row echelon form of A. In other words, so I say here, how do you get a basis? How do you get a basis for the null space of A? Well, you just take A, you reduce it into row echelon form. There might be some free variables, you bust those out. And as you bust out those free variables, what is left behind is your basis for your null space. And the number of basis vectors is exactly the same as the number of free variables. So for every free variable, you'll have another basis vector. Free variables correspond to unpivoted columns in the row echelon form. Right. So anyway, so to find everything you want to know about the null space, guys, it's right here on one line. Just have to know that line. That summarizes everything. Row space, very different. It's still a subspace of Rn, just like the null space was, but it is a completely different subspace. It is going to be something totally different. It's living in the same universe, but it's a different thing. I mean, it would be like, this universe of R3, this plane of this folder, that's a subspace of R3. It's a 2-dimensional subspace. Well, here's another plane that's a subspace of R3, but it's not the same plane, right? They're going in different directions. They're oriented differently. That's the same thing here. My null space and my row space, they both live in the same universe, but they don't have to have anything to do with each other, right? The row space is just the span of the rows of A. You just look at your matrix, just take those rows, write them down, and the span of those rows is your row space. And the way that you find your basis for the row space, it's kind of a nice thing, because you do the same ERO calculation. You bring A into row echelon form again, right? So you don't have to do, usually you're going to get asked to do all 3 of these. So the good news is you don't have to do the EROs 3 times. You just do them once, and it's the same row echelon form. But then what you do with that row echelon form is different for the row space. Instead of setting up free variables and busting them out, now for the row space, you're just gonna literally grab the pivoted rows. Write them down, make a list. You will potentially have zeroed out some rows in the meantime. And if that happens, no worries, you just ignore those. And it's just the pivoted rows that are left behind. And of course, the number of pivots is better known as the rank. That's the dimension of the row space. Right. So we had an example on Tuesday. Maybe I can write it down again so we could review these concepts with this example. And then I also want to talk about the column space too. So let me just put this example here. But before I do that though, is everybody okay with what's up there? Honestly, if you know what's on that half sheet of paper right there and you have it learned really well, you are in great shape for these last 3 sections of chapter 4. So, print that thing out if you need to, make flashcards out of it. Put it under your pillow every night for the next 2 weeks before the test, whatever it takes to like get this learned well. That is a nice summary, and all in one place, everything that you would need to know. So, but let's go back to this example. I had this up the other day. So let's take A to be the matrix 1, 2, 6, and the second row is 2, 1, 6, and then 0, 1, 2, and then 1, 0, 2. So this was the matrix we had. And really quick, can somebody remind me what's the size of this matrix? What's the rows and columns?
2 by 4.
Careful. How many rows, how many columns?
4 by 4.
4 by 3. 4 by 3. So 4 rows, 3 columns. And as you know, the first number is the M and the second number is the N. So M is 4 and N is 3. Okay. So again, to figure out the null space or the row space, we're going to do EROs and bring this matrix into row echelon form. I'm going to just skip the EROs and cut to the chase here, get to the final row echelon form, which is really just the first row and the third row. The other rows all get zeroed out. I think I might have shown the full details of that on Tuesday, but for today, I'm just going to abbreviate what the final result was. Notice that there's, if you think of these columns as associated with X, Y, and Z, you have only one free variable. And you might remember from, so we have one free variable, so the nullity of A is going to be 1, and the basis, this was, again, you can go back to your notes from Tuesday, you'll see that we have one basis vector for the null space. It was -2, -2, and 1. Yeah. Okay. So that all comes from setting up the free variable, solving it by back substitution. We did all of that before. I don't think I'll repeat that right now, but we can see that this is basis for null space. Let's just make sure we keep these things straight. That is a basis for the null space. It is one dimensional. It is one dimensional. Okay. So then for the row space, see, once you have the row echelon form, you can literally just immediately write down the basis for the row space. So the basis for the row space of A is, what does it say over here in the handout? It says go to the row echelon form, take the pivoted rows of the row echelon form. I know that's a little hard to read in the back, but that's what the handout says. Take the pivoted rows of this row echelon form. And I'm going to write them as rows, since we are talking about row space. So I drew the null space vector up and down, and now I'm writing the row space vectors horizontally. It really is not wrong which way you configure it, but I like to draw rows as rows and columns as columns. Yeah, Edgar?
So here in this example, it just happened to be the same, well, it's the form of the rows after they've been brought to row.
Yeah, exactly. And so this would be a basis for the row space of A. Now, it turns out there is a little theorem that if you wanted to, if you wanted, you don't need to do this for the row space. The story for the column space is going to be different. But for the row space, if you want to, you can take those pivoted rows and go back to the original matrix A and just take the corresponding rows as your basis instead. In other words, another perfectly good basis for the row space here would be 1, 2, 6 and 2, 1, 6. You could do that. Okay, but I like to just take the pivoted rows of the row echelon form. So, because that's the matrix that I've already worked on, and you know, it's just perfect. It's perfectly good to just use this. And then you can see, of course, that the rank is 2. So the dimension of the row space here is 2. The dimension of the null space was 1. And remember that the rank is just the number of pivots. The nullity is just the number of non-pivots. So we talked about this on Tuesday, that if you add up number of pivots plus the number of non-pivots, which is the rank plus the nullity, you have to get the entire set of columns, which is in this case n, which is 3. So 2 plus 1 is 3. That's totally consistent with this this so-called rank nullity theorem. So that was a big result we tried to look at on Tuesday as well. Okay, I'm still kind of recapping. So if there's questions about any of this, just feel free to holler out if there's anything lingering over from the other day. Okay, so lastly, there's a third subspace, and I barely had time to do much with it on Tuesday, so I will just briefly talk about it now. It's not that crazy, but it's the column space, which is sometimes written call space. And as you can see from my handout over there, this is just the span of the set of the column vectors of A. Right, so it's just the span of the column vectors of A. And because it's a span, remember, anytime you take the span of anything, you automatically have a subspace. So this guy will be a subspace. But I always like to ask, what is it a subspace of? If I think about columns here, if you look at the columns of this example, each column has 4 slots. The 4 is coming from the M value. I know it's a little weird, because like, wait a minute, I thought the M was the rows. But yeah, M is the number of rows, but that's what determines the number of slots in each column, as it turns out. So it's actually, this column space is actually a subspace of Rm. Right, there's a column, there's a column, and there's a column. Right, each column has 4 slots, M slots in it. The number of columns is only 3, but each of those columns lives in the universe of the R4. And so it's a subspace of Rm. So notice that that's different than the row space and null space. Okay, row space and null space are both subspaces of Rn. Now the column space is the subspace of Rm. So that's a difference. But how do we find a, well, let's look at our example. In the example, the column space of this matrix that we have over here, it's the span of those columns. Let me just write them down. 1, 2, 0, 1 is the first column, comma. The second column is 2, 1, 1, 0. And another comma, and then the third one is 6, 6, 2, 2. So it's the span of those 3 column vectors in this case. Now, since there's 3 columns here, does that mean that the column space will be 3-dimensional? Remember, the dimension is just how many vectors are in a basis for your space that you're looking at. So my column space, here's three vectors, right, that are part of that column space. But are they a basis for the column space? Or could something go wrong? Anthony?
The third vector is a linear combination of the first two vectors.
Okay, in case you couldn't hear that, what Anthony pointed out is that the third vector is a linear combination of the first two. I honestly can't see that just immediately without doing a little work in my head. But I do know that I have this handout that over here, it tells me that the dimension of the column space is the rank of A. We already know the rank of A is 2. So therefore, 3 vectors is too many. And in fact, when K is greater than the dimension of your space that you're working in, you already have a no on the Li question. And this is what Anthony was pointing out, is that the third vector is really a combination of the first two. So there is going to be a linear dependency there. So then the question is, how do we get a basis? Okay, well, that's on the handout too. It's all here, guys. This is all you need to know. I know this is kind of small writing, but let me just read out what it says here. First thing is good news again. You just have to bring the matrix into row echelon form. Same thing we've already done for the null space and the row space. So here's the matrix. And what does it say here? It says, take the columns of A corresponding to the pivoted columns of row echelon form of A. So I did not say just take these columns. I said take the corresponding columns from the original matrix, which in this case would be the first two, because it's the first two columns that have pivots. So my basis here, my basis for the column space of A, if we believe what's on the handout, if we believe that handout, then what we're looking for is a basis for the column space of A by simply taking the corresponding columns from A itself. So we have to go back to the original matrix is what I'm saying here, guys. And grab the first two columns of A. So there is a little difference between row space and column space as far as getting the basis. You know, guys, when you do EROs on a matrix, when you do elementary row operations, you're really just making linear combinations of the rows that you already have. You're not changing what they span. You're not changing the row space of your matrix when you do EROs. But when you do EROs, you will mess up the columns. And so it would not be fair to take the pivoted columns from the row echelon form and call those your basis for your column space. That won't work. Oh, I could give you an easy example. If you don't believe me. You believe me, don't you? I bet you believe me, but I'll just show you a super, super easy example, right? So let's suppose this is my matrix. And I'm thinking about the column space of this matrix. Well, it would be the span of these two columns. The two columns are exactly the same. So your column space basis should be 1, 2, right? But if you were to get careless and say, I'm just going to do an ERO on it, zero out that bottom row since it's just -2 times the first row, add it to the second row, and then I get it into row echelon form, which would be this. If I decided, oh, well, I'm going to just take the first column of the row echelon form, I would have written that down as my basis vector. And this vector are not even pointing in the same direction. They are not at all exchangeable. I can't say, well, instead of this, I'll write down this, or instead of this, all right. This is the right answer, right? As soon as I do EROs, I will mess up what the columns are spanning. So that little example shows us, right? The span of these columns is really just dictated by the vector 1 and 2. But the span of these columns is dictated by the vector 1, 0. And they're not the same. We have destroyed the column space by doing EROs. So that's why there's a little extra asterisk over here. It's basically, it's not really an asterisk, but a little extra comment about how do we get the basis for the column space. We can get the row echelon form, but then we have to take the columns that correspond to the from the original matrix that correspond to the pivots. Now, by the way, if you really wanted to, you could say, well, if I want to figure out the column space of this matrix, why don't I just transpose the matrix? That switches rows and columns. So then I'd be looking at basically the rows of the transposed matrix, and I could just do the row space of that. That's true. You could. You could transpose the matrix and say, instead of working with A as it is, I'll look at A transpose. Because the span of the rows of A transpose is literally the same thing as the span of the columns of A. So just as a plan B for anybody out there who doesn't like this, what I'm saying over here for the column space, your plan B is take your matrix, you want to find the column space of it. All right, transpose the matrix first, then find the row space of that by just doing your EROs and taking the pivoted rows, and then re-express them as columns again. So, and that would be perfectly fine. Why don't we do it that way? I mean, why don't we just figure out column spaces by doing transposes of row spaces? It seems easy. Well, the reason is because we've already done these EROs. If you transpose the matrix and then you're like, well, now I'll find the row space of that transpose matrix, well, you're going to start all over with EROs again. Because the A transpose matrix is going to have a whole different set of EROs than this one did. So it's not that it's wrong to do that. It's just going to be more work. That's all. It's just easier. All three of these, the null space, row space, and column space, we can use the same row echelon form for. We don't have to like go back and then do another a different matrix and calculate EROs again. So that's the reason that I generally don't advise people to convert a column space into a row space by using a transpose. But it wouldn't be wrong. It would not be wrong to do that. Is that clear? Clear to everybody? Okay. I think I've pretty much said everything I need to say. By the way, isn't it kind of interesting? The dimension of both the row space and the column space is just the rank of A, which is in this example 2. See, I've got 2 basis vectors here for the column space, and I've got 2 basis vectors here for the row space. Notice I wrote the rows as rows, I wrote the columns as columns. That's generally the way to help yourself keep this all straight. But it's interesting that those dimensions are the same, even though they live in different universes. Right, the row space is a subspace of Rn. The column space is a subspace of Rm. And we can see it here, right? These 2 row vectors live in R3, but these 2 column vectors live in R4. So that big universe has changed depending on whether you're doing rows or columns, and yet the number of vectors that's in your row space or column space is definitely the same. Yeah, please.
So once you do your EROs, does it matter which one you do first, like null space, row space?
Oh, you just do whatever they ask you to do. Sometimes on a test, I'll say, give me a basis for the null space of this matrix, and that's all I ask.
Okay.
Or if I ask for the row space, then you do the row space. Yeah, it doesn't really matter. Yeah, it doesn't really matter. Other questions so far? Okay, guys, I have one last thing I want to do. I'm gonna go ahead and turn this off, but this is a really nice handout. I really tried my best to like put some very, very important stuff all on this one page. So it's in Canvas here, recap of 4.6, 4.7, sorry, 4.6, 4.8, 4.9. Yeah, okay. Let me see if I can get that to go away for me so I have a little more room to write. I want to do one last thing in chapter 4. If my papers don't fly away on me there. Thank you. Thank you so much. One last thing I want to do, guys. I would like to briefly talk about section 4.10. 10 sections in this chapter. Oh my goodness. This, however, this section will not have any homework. It is a 1-page section, and in my case, it is a 1 whiteboard section. All I want to do now is it's been a few lectures since we looked at do you remember the invertible matrix theorem?
Oh, no.
with A, B, C, D, E, F, G, I think it was. I would like to revisit that theorem now and add a few more items, now that we have some of these concepts of Li and row space and all this stuff. There's some more things we can add to the list. So let's just do that. This is going to be called invertible matrix theorem. I'm just gonna say revisited. I'd like to revisit this invertible matrix theorem with you. Okay, so let's just remember, you know, how it sets up. We have A, which is an n by n matrix. So at least for this, the matrix is a square size. And then what it said, if you remember, is the following are equivalent. And it was a list. It was a big list of statements that you might remember. So the point of me presenting this to you guys, by the way, is this is entirely conceptual. I just want to help you sort of glue together some of the concepts from, say, the first part of the class with these more recent ideas. There's no homework on this. There's not really any problems to do. This is more about just trying to really wrap your head around how all of this stuff fits together. That's the reason we're doing it. And I won't relist everything that we had done in this list earlier, but I'll list a few of the important ones. Obviously, the first one is important. A is invertible. I have to write that down again. And then I'm going to skip over B. I don't need to write that one down, but I am going to write down C. And C says that the system A times X equals 0 has only the trivial solution. So that one I am going to make a reference to in a minute. So that would be called X equals 0, the trivial solution. And then there was an item in the list about the rank. Can somebody remind me what was the rank of an n by n invertible matrix?
N.
It is n. Okay, so we'll add that one to the list again. Let's see, what else might be useful for us? Well, we had the one that everybody loves to use is the determinant one. That was statement G. So the determinant is not 0. So we have this list so far. And what I would like to do now is add items H, I, J, K, L, M, N, O, and P. Okay. Whoa, so it's a big improvement to our theorem that I'm about to give you. Okay, let's start with H. I am interested in part H. I'm wondering, so we have not looked at this before, but for an invertible matrix, does anybody have an idea what the nullity would be? Actually, I don't want to put that screen down again, but if you can see on the sideboard, there might be some helpful stuff. This is just off of that hand. I know it's hard to read, but in particular, there is something that stands out in this thing I've displayed that might help you figure out what the nullity of the matrix should be.
0.
0, how come?
You're gonna have the full rank.
The rank is n, right? And what's that box say? I know it's hard to read. Rank plus nullity adds up to n. So if the rank is n, then the nullity is 0. That's right. So for an invertible matrix, the nullity would be 0. That's statement H. It's a nice one, very easy. The next one is actually just entirely related to this. So if the nullity of the matrix is 0, that just means that the dimension of the null space is 0, because nullity is just dimension of null space. I don't know if I've ever really talked about what it means for something to be 0 dimensional. This would just mean that there is no basis vectors. As I thought every vector space would have a basis. Well, there's one vector space out there that doesn't have a basis at all because it's so incredibly trivial. And that is just the 0 vector itself. So we can actually write down that for an invertible matrix, the null space is just only the 0 vector. Something that is 0 dimensional must already itself be 0. Now, if you don't like that way of thinking about it, I can give you another way to think about it, which is statement C. Statement C, how do we find the null space of a matrix? Well, we're really looking for solutions to AX equals 0. If you remember what the null space is, that's what you're doing. And what does it say here? If A is invertible, what solutions are you going to have for your system? Oh, it just says X equals 0. So your null space is just the 0 vector. So the best way to remember this is just that when your matrix is invertible, you have a tiny null space, as small as it could be. It's just 0 alone. Okay, so far so good. Let me talk about, so that's the null space. Let's try and talk about the column space and the columns here for a minute. So statement J is that the columns of A, so if you think about those columns of A, if you were to take an invertible matrix and row reduce it, you would get pivots going all the way down the diagonal, right? Which would mean you would get no free variables out of those columns. So if you lay your just take the whole matrix A and like chop it up column by column and lay those columns down and do your EROs, you would have no free variables. When we have no free variables, when we row reduce a set of vectors, what do we learn? What does that tell us about that set of vectors? They are Li. They are Li. They are linearly independent, right? So that was our test for Li. Put your vectors into the columns of a matrix, do the EROs, and if you have free variables, they're LD. If there's no free variables, they are Li. Well, guys, here you will have no free variables. You can't. Look how many pivots you have. You have way too many pivots to even have a free variable at all. There's no free variables, so these columns will be Li. No free variables at all.
Nice.
So the columns are L, and that is nice. That is really, really nice. So that's J. Statement K is going to be about the call space of A. So I'm sticking with the columns for a minute. But let's think about what the column space of this matrix would be. Now that, by definition, that's the span of the columns. Right? And let's remember, I know it's hard to see, but when I look at the column space here, its dimension is just the rank of the matrix. The rank of the matrix, which by the way, is n, right? So we're talking about an n-dimensional space here within the universe of Rn. So what is it going to be equal to?
N, better.
Its dimension will be n, but what does this literally equal as a set? The span of all these columns gives you something that's n-dimensional. It actually has to be the entire Rn. It has to be the full universe. Okay, guys, let me, I maybe haven't made this point very well previously. This universe that we're sitting in right now is R3, right? Let's suppose I ask you to give me an example of a two-dimensional subspace of R3. A two-dimensional subspace could be any plane. Okay, this plane, whatever. These are all examples of two-dimensional subspaces. What about three-dimensional subspaces of R3? The problem is that R3 itself is already three-dimensional. There isn't anything sort of smaller inside of it that's still going to be three-dimensional. The only, I guess here's the punchline, the only three-dimensional subspace of R3 is itself the entire R3. There's nothing else it could be. So the only n-dimensional subspace of Rn, that's what this column space is. It's n-dimensional because it matches the rank, and it's a subspace of R, that's normally Rm, but here m and n are the same. It's a subspace of Rn, so an n-dimensional subspace of Rn must actually be Rn, equals Rn, literally equal to it. It's as big as it could be. The null space is tiny, the column space is humongous. It's as big as it could possibly be. All right, So that's the point about the column space. Let's add one more comment here. By the way, another way of I'm gonna put this in other terms. This is just saying that the span of that the columns of A, they span Rn. They span the full Rn. It's not some smaller subspace, it's the full Rn equals Rn. So if I take the span of the columns, I get the full Rn. So let's see here. My columns are Li. My columns span Rn. What do you suppose I'm going to say next? If I have a set of vectors that is Li and also spans my space, then that is better known as a basis. Thank you. Yes, the columns form a basis. The columns of A form a basis for Rn. That's exactly right. That is exactly right. So they are Li and they span the whole Rn, so they are a basis for Rn. So J, K, and L have to do with the column space. H and I are kind of about the null space, and now J, K, and L are about the column space. Well, the next three, M, N, and O, are going to just be literally the exact same statements about the rows. So everything we just said about the columns will also be true about the rows in a case of an invertible matrix. So I'll be able to say that the rows of A are Li. That's M. Item M, the rows of A are Li. The row space of A, well, that's the same n-dimensional thing that the column space was. It has the same dimension, which is the rank. So the row space of A is equal to Rn. And finally, a statement O, the rows of A form a basis for Rn. Absolutely. So everything we said about the columns, we can also say about the rows. So this is quite a bit, I guess 8 more statements here, 2 things about the null space, 3 things about the row space, and 3 things about the column space. Awesome. Good enough? Questions at all? Do we have enough of an alphabet to handle all the statements we're going to be making this semester? I don't know. We're up almost to 2/3 of the way through the alphabet with that, but there's actually much more we can do. There's much more we can say as we keep doing more results, guys. We can keep adding to this list. It's a really, really nice list. It's a famous theorem in linear algebra, no doubt about it. Before we take a break tonight, guys, I want to do one example, and this example that I'm going to do is very similar to one of your homework problems for Sunday night. So I've just changed the numbers basically, but otherwise it's almost exactly the same as one of your homework problems. And it's one that I always get asked to do. And so since many of you may not have had a chance to get all the way up to 4.9 yet, my guess is maybe it'd be nice if I could just help you out in advance with this. So consider this, this is an example, and maybe I can actually tell you which problem it is. I don't remember right off the top of my head. I think it's in 4.9. The book is falling apart. Yeah, it's like, I'll just say it's similar to, I'll just say C 4.9 number 14. It's one of the homework problems for Sunday, I believe. So this will help you with that problem. But I'm going to change the numbers. So you'll have to look at the homework problem and make the translation. Suppose that A is a 4x10 matrix. This is a theoretical problem, by the way. A is 4x10 with nullity of A equal to 6. Let's assume that the nullity of A is equal to 6. What I would like to do here, guys, is I would like to show that the call space of A is equal to R4. like to try this problem. Now, nothing that's over here will help us, because of course, this isn't even a square matrix. So I can't be thinking about invertible matrix theorem right now, so I just wanna, I know we just talked about that. This is kind of more of a general problem, and I have a matrix that's 4 by 10. I would like to show that the column space is equal to R4. So maybe it would be helpful if I showed this slide again. Because everything you need to know, like what's the dimension of the column space, what's it a subspace of, all that stuff, that's gonna be relevant here. That's gonna be important, right? So what do we know for this matrix? What do we know about the column space? So obviously, we know it's the span of the columns. But what do we know about, what is it a subspace of, and what will its dimension be? I guess that's my really what I'm gonna ask you guys. What's it a subspace of? It says Rm on the handout. What is M here? M is the 4, right? It's the first number here. So just note, so now I'm doing the solution here, guys. The call space of A is a subspace of R4. Now, being a subspace of R4 doesn't make it equal to R4 automatically. So I'm not ready to say I'm done yet. I have to still explain this a little bit more, right? But for sure, from what we've said so far, we have a subspace of R4. Right? But let's go a little bit further. What else can we get off of this handout? What's the dimension of the column space going to be? Dimension of the call space. What's it say over there? The rank says rank. Do we know what the rank is? They didn't give us that, but what did they give us? They gave us the nullity. Is there a relationship? Oh, you guys can't see it. Blocked off the bottom of the screen there. The relationship, guys, they give us a beautiful relationship here. If you add the rank and the nullity together, you have to get n. What is n here? N is 10. So n is 10, the nullity is 6. So can we figure out the rank? It should be 4, right? So this is the rank of A. And the rank of A is 10 minus the nullity of A, just from the rank nullity theorem. But nullity of A is 6, so we just get 10 minus 6. So it is 4. The column space is 4-dimensional. Oh, now we're getting somewhere. It's a subspace of R4 that is 4-dimensional. What did I just say a few minutes ago? We're living in the R3 universe, and I asked you what could be a 3-dimensional subspace of R3. The answer was the only thing that you could have would be the entire R3, right? Guys, if I have a 4-dimensional subspace of R4, it is R4, right? These two facts together, the fact that it's a subspace of R4 and its dimension is 4, tells me that my column space, putting this together, my column space is equal to R4. So I will just say, thus, the call space of A is equal to R4. That's it. The two things together allow me to make that conclusion. Questions about that? Seems okay. Let me ask you a quick follow-up question, then we'll take a break. Follow-up question is going to be, is the row space of A, is that going to be equal to R4? Now, let me just start by saying that the dimension of the row space is literally, it's the same thing, right? The dimension of the row space is also the rank. The rank is all this stuff, right? So as above, the dimension of the row space of A, that dimension is equal to 4. For sure. No worries about that, yeah? That dimension is equal to 4, but does that make the space equal to R4 just because it has the right dimension? I know lots of things that are 4-dimensional. P3 of R is 4-dimensional. M2 of R is 4-dimensional. There's gobs of other subspaces that would be 4-dimensional, right? So just knowing that something is 4-dimensional is not alone, it's not enough to say that, yeah, this is equal to R4. Just like over here, just this calculation alone is not enough to say that the column space is equal to R4. I had to know that not only is it 4-dimensional, it was a subspace of R4. That had to, both facts had to be there. Is the row space a subspace of R4? When in doubt, let's hold our little chart here. Row space is a subspace of Rn. N is 10. And guys, actually, if you think about it, it might even help. Write down kind of the form of this thing and look at the rows. Right? Look at a row here. If the row space was equal to R4, then the rows should have 4 slots in them. But you can see that these rows all have 10 slots in them, right? So I'll just say here, however, actually should do this in blue. It's still part of the solution. However, row space of A is a subspace of R10. And so the answer then, guys, is going to be no. If you wanted to say something that was correct, what you would need to say right now is that the row space of A is a 4-dimensional subspace of R10. That would be fine. But saying that is equal to R4, guys, in math, the equal sign is really strong, a strong thing to say, right? Saying that one thing is equal to something. It's not equal. So I would not be able to say that the row space of A is equal to R4. All I can say is that it's 4-dimensional and it's a subspace of R10. Those things would be correct. Okay. If you follow this, you'll be in great shape to work on this homework. I think in the homework, it's like a 6x3 matrix or something. It's the dimensions are different, but it's the same idea. It's exactly the same idea. Okay. If there's nothing else for now, guys, why don't we take a 10-minute break and let you guys stretch your legs a little bit, decompress from the math, and we'll get back at it in another 10 minutes. Yeah, go ahead. Don't tell me. I already know that. Look at him, I have
The last one, my I went it was like -1,000, -2,000. I was like, oh, I already know what's wrong.
Oh, okay, I'll wait. Sorry, it's a second place. Can
So it was.
I erase the side?
200.
Oh,
I hate the 200.
So it is my last one.
First is the Casa. What? First is the Casa. Good, okay. Guitar. Yeah. And the only reason Casa that follow is because now it's us. Similar, but the same. Yeah. There was like. I okay, so draw. See this research gets drawn. Well, that's just right.
It depends on the chemistry.
Yeah, you know, that's good.
So,
That's been able to see that fast road curves.
so I'm pretty sure like the past one I get.
It is only so far they only class that so why you know what I built that out as well.
So moving right now, I'm at 62.3%.
Where did be always at 43 they talk mostly. That's where I'm at right now.
You're finding each other, right? Yeah.
When is the?
You said 2 weeks from today, but I thought it was on Tuesday.
I'm not even ready for that.
Takes a long review.
Right.
It's easy to get lost.
Yeah.
Like, wait, we're done.
Yeah.
Surgeon. Yeah, they'll adjust.
Yeah. That's gonna be.
That's gonna be. Yeah, Mr.
Yeah, that's homework, I'm gonna like, be with him the whole time. Like, you do this thing.
You're gonna what?
I'm gonna have to bug him for it. like, all the time.
Sure. That's probably the best part. Yeah, that's why I didn't try to hit close hours. It's just good, even if you don't get the answer there. like,
Yeah.
Right off the bat, but you're hearing like the language again. you're like,
Yeah,
oh,
yeah, it comes
Something-
fast.
Yeah, just reinforces, so. Makes you a little
I
stronger.
thought that was like, oh, fuck.
I know.
I'm like, wait, what?
Yeah, but.
Oh,
Like that.
So is that like an Apple? tablet?
No, it's Samsung or Samsung or Android.
I don't know, I'm like so impatient, like if it gets messed up.
Oh, really?
Yeah, 'cause-
These like the old school way.
Yeah,
I got you.
it's kind of like more like the way I see things, it's, I don't know, I just with a book too.
Yeah, like pen and paper.
Like at home, I use the computer, but.
Sure.
So we just
Yeah.
like this.
Yeah, I kind of made the switch like 2-3 years ago. Sometimes I'll bust out paper. You know, it's like kind of a last second thing, but. This just helps me in the sense, it's like I don't have to like buy another notebook.
Yeah.
or-
Go over it now.
Yeah, I guess that's really. And I do like some of the just little features. I'll just use like OneNote, but different colors like stick to my
You
brain.
can zoom in.
Yeah, and then I highlight stuff, so that kind of just helps like
Mhm.
sticks out to me a little bit.
Yeah.
That's just.
But, yeah, makes sense.
So.
I'll probably get one later. I'll probably get one later.
That's okay, yeah.
A lot of people have them. but I'm sure.
Pressure.
Yeah.
Yeah.
I know
Yeah.
that there's some pressure.
Yeah.
The negative side of art.
Huh, another one. Looks like she's like posing for the.
She is, my wife puts her against a backdrop.
Uh-huh,
Like a little
okay.
blanket backdrop.
Oh, she's.
Oh, yeah, not me.
Okay, no, I know, like, I think I took her somewhere.
Regarding. No, yeah, she
She
does, yeah,
does them herself.
yeah, just like right on the couch.
That's very creative.
So she actually got an offering from
Nice.
Abercrombie or Fitch, whatever. Oh, we'll pay $5,000. Take
It's
photos like that.
very like creative. I didn't know, I thought you were taking her to go
No.
take those pictures.
She does like the little thing. That's her 2 months.
Uh-huh.
A little fist bump.
Face like goes up the wall.
She is. She's my chunky little woman.
She's
She's,
a pretty good Tokyo.
when she, the first time, when she really started to plump out.
You know.
And I was just letting her sit with like, just
Yeah.
carrying her diaper. And she sat on me, like just on my leg, like looking at me. And the sleep was just, oh, me like rolls. I was like, oh yeah, something grabbing me. I'm like, actually, she's working. Cause, you know, that's kind of the first time I like. Let her eat a diaper and
Oh,
roll
okay.
free. Yeah,
Okay.
yeah.
They feel different. It's good when you
I'm like, oh god. The problem.
Yeah.
Quite skeptical.
My daughter was like.
This girl, you're free.
Uh-huh.
Yeah, I don't blame her, especially if she's in like one
Oh, yeah.
day, like
Oh, yeah.
when you unleash them, they like kick their legs and stuff.
Thank you.
Yeah.
The vertical matrix is just.
Dude, I was this guy playing high road. You laugh.
Yeah. Learning something every day, it seems like. Every little.
I know,
I'm sure you've learned that,
I
like,
just kind of get lazy.
every day there's like something that she thinks out.
Oh,
It's
yeah.
a good thought.
And she just started doing like pushing her
It's
tongue
not a bad
against her
thought.
lips. It's really cute.
Yeah.
And you will notice that you are.
Or she started touching her head. Where did you put that?
Oh, yeah, somebody
She's
grabbed
like,
it
who
from the
are
head.
you, who are you watching? Who are you watching?
Gradually.
I think it's for me.
$6. They have like $6.
I was just kind of a brat, like it's cute to get sick.
Yeah.
Just fussy.
I do not.
I wonder why. Maybe it's just the food. I mean, it's like.
I'd probably kiss her to death too, like my beard. rubs against her.
Oh, yeah, she feels that.
She couldn't scream. Hates it. He's tough. I call it, I pester her. Just up in her face.
You have to.
My wife yells at me.
She's like, don't get too close to her.
Well, I'm Andy, you can choose the jobs correctly, you may be only,
That's,
thing. Do the same.
I don't know, they can be exact.
It's the same thing.
He's here. FaceTime today.
She, she believed it had water when she was born. Or she had hair.
No, she didn't really have it.
It's different, like in every picture.
Is this even my kid?
Oh, that's it. Oh, I don't even do that. Look at that. Lucas was the thing, bro. I don't even. I think like, wait, all right. It's like, bro, you gotta do it after that.
Lucas didn't know how to do that.
I still call my kids my baby. The other day, my daughter's like, "Mommy, I'm not a baby."
I know.
I'm like, "Yeah, you're still
Wow,
not."
it's not.
What's the bad name?
Yeah.
Thank
you.
Yeah.
All right, everybody, I think most folks have made their way back by now. I think I'll go ahead and pick things back up again. Sorry for like all this long lecture time tonight. I am trying to get through some material, so you have some stuff to chew on for the weekend. Next week, we will do some group work and we'll also have more time for some of the homework that's coming up. I noticed no problems made it onto the board over here. I'm guessing that's because we're a little early. Yeah, it's only Thursday and I'm yeah, if people haven't started it yet, it wouldn't be shocking to me either, and that's okay. It's okay, I understand. So take the weekend to get on top of that, but you do have to promise me that you will come in Sunday into Zoom with questions if you have any, right? That's a pretty important assignment. So don't just say, oh, he's out of town, I'm not gonna bother with it. I will be so happy to just talk about math questions. I'll be resting my legs and everything by Sunday. So I will be very happy to just sit there in front of my computer and talk. So
To do a Zoom meeting on top of somehow saying.
I'm not gonna do that because you won't be able, all you'll hear if I try to have office hour up there, the wind blowing 30 miles, I just checked it again, it hasn't gone down. 30 miles an hour wind, can you imagine how the microphone would be? You wouldn't be able to hear anything. So yeah, I'll wait till I come down. But that's a good thought. I always tell people, you know, that I'm a theoretical mathematician. I could easily just, all I need for my research is pencil and paper. I could go on the top of any mountain and just do my work. So I don't need to take a computer with me or anything. But anyway, I probably won't be doing that this weekend. Yeah, so anyway, the good news here though, guys, is that we have made it through chapter 4. modulo this homework assignment that we still have to do. We're pretty much finally done. There was a lot of material there, right? Starting with subspaces and vector spaces, and then we had to talk about span and Li, putting that together into a basis, dimension, and then all this stuff we've just done today with row space, null space, column spaces. There's a lot of material in chapter 4. No doubt about it. It'll be at least 50%, maybe even a little bit more of the next midterm coming up will be based on it. And the stuff from chapter 4 is going to continue to get used. It's one of the things I like about this class is that we keep using the stuff we're learning. You're never going to feel like, well, why did we learn that, right? It all comes full circle back into the applications again. So normally what I would do right now is I would start chapter 5. But as I've told you, I'm going to give you guys time this weekend on top of this homework assignment. You also need to carve out about 70 minutes to take notes on a video that is really about chapter 5, at least a good start on chapter 5. So I don't want to start talking about chapter 5 before you've had a chance to watch that. And so I have decided to jump ahead. I've never really done it this way before, but I think it's going to work just fine. I'm going to jump ahead to chapter 6 right now. And then we'll go back next week, we'll go back to chapter 5. Chapter 6 is called linear transformations. So I'm going to take a little bit of time here, pretty much the rest of today, to try to explain this as best as I can. And you will have homework from this first section to do for Tuesday. If I don't get a chance to cover everything, just do as best as you can with it, and then we'll take questions on Tuesday. Okay, that's going to be the game plan. Guys, up until now, in chapter 4, we were always looking at just one vector space at a time. So one example, I would do polynomials. Then I'd put that down and I'd do another example on matrices. Then I'd put that down, I'd do another example in R3. Right? It was just one example at a time. We jumped around a lot with these examples, but it was only one vector space at a time. Well, as you can imagine in math, math is all about relationships between things. And in this case, we're talking about vector spaces. Linear transformations are going to be the vehicle that allows us to explore relationships between vector spaces. Believe it or not, knowing how polynomials work can actually help us understand how matrices work, and vice versa. And we could take any of our other examples and make that same kind of a statement. And the key tool to doing that is something called a linear transformation. This is super important, especially in computer science, because basically a linear transformation is basically a function that takes vectors in and takes vectors out. And just to give you one really quick example in computer science, your screen that's got all those pixels on it with some kind of a graphic design, as that image moves, say it's a movie or something, it's changing, you are actually creating a function that says this pixel is going to go there and this pixel is going to go there. And all within the framework of this screen, you are performing a linear transformation to take one image and turn it into another image. So certainly people that have an interest in the technical aspects of computer graphics would find this kind of a topic to be quite useful, quite relevant. But let's give the definition here first of what is a linear transformation. And then we're going to pretty much try to do a bunch of examples. So a linear transformation, give the definition. A linear transformation is a function. And I'm going to say, we're usually going to use a t for this function. And it's a function that goes from one vector space V to another vector space, which I'm going to call W. So these are vector spaces. V and W are vector spaces. They don't have to be the same vector space. This could be inputs are coming from polynomials, outputs of matrices. Or it could be inputting a calculus function and outputting a physics vector, right? So the two vector spaces, at least in the setup of the definition, they don't have to have anything to do with each other. But this function can't just be completely random. There are a couple of rules that this function has to satisfy. It basically needs to respect the vector space operations. Sorry, I got it. It needs to respect the addition and the scalar multiplication in the respective vector spaces. So let's write that down. Okay, so I'll just say it's a function such that two things are true. A and B. A is going to be T respects addition. T respects addition. So what do I mean by that? What that means, guys, is that if I take T of V1 plus V2, it should be the same as T of V1 plus T of V2. And this would be for all V1 and V2 in V. So the input vector space is V, and the V1 and the V2 are being inputted into the transformation T. So remember, T is just a function. Call it F if you wanted to, but we usually call it T here. So T needs to respect addition. The second thing is that T has to respect, so T respects scalar multiplication. I'll draw that as a dot. And so you guys probably know what I'm going to say. T of K times V1. So if I have a scalar K and I do a scalar multiplication, I have to be able to pull the K out and write it as K times T of V1. And this is going to be for all K in the real numbers. The K is a scalar, so it'll be in the real numbers. And again, V1 is still a vector in V. So T will respect addition and scalar multiplication. And it makes sense that that should be the case because we're working in vector spaces, and vector spaces have two operations, addition and scalar multiplication. This is kind of going to remind you of checking that a subspace is closed under addition and scalar multiplication. It's kind of it's a two-part verification here that we have to do. So that's at least a nice little warm up of the definition, but I want to do examples, of course. So let's get an example up here. So let's define T to go from R3 to M2 of R. So the way I'm looking at this, I'm setting up my V is R3, my W is M2 of R, but I have to give you a formula for this function, right? So I have to actually write it down. I'll say via. And then what I'm going to do here, guys, I'm going to take T of, let's say, little a, little b, little c. And I have to spit out a 2x2 matrix. So by the way, all of this that I'm putting up here on the board is given, right? I'm just giving you this setup. And the 2x2 matrix has a 0, and then an A minus B plus C, and then a negative A plus B minus C, and then a 0 again. That would look something like that. So I'm plugging in a vector in R3, and T is a function that takes that vector and outputs something in the W vector space. And in this case, that would be a 2x2 matrix. So all of this has to be given. I have to know what is V, I have to know what is W, and they have to tell you what the formula is. Otherwise, you don't know what you're doing. Right? You have to have the formula there. And what I want to do here is I would like to show that T is a linear transformation. I'm going to get a little lazy about writing that out all the time. And so there's a shorthand way to just say the same thing, which is that I'm going to show that T is linear. So you'll see me just say, oh, T is linear. What I mean is it's a linear transformation. It respects addition and scalar multiplication. Okay, so let's come over here to do the solution. I want to give myself enough room. And guys, you are going to want to format this write-up very precisely. Just like when we were verifying subspaces, I had a very sort of template, I had a very rigorous template that I wanted everybody to follow how to write this stuff down. That's also true here. So this is kind of a proof, so to speak. We're showing that this is linear. So we're gonna wanna write this down very carefully. And we're gonna do it in 2 steps. First of all, T respects addition. We'll start with that one. And how does that work? Well, I have to show that this first equation is true. T of the quantity V1 plus V2. So let's start with that. T of, let's say ABC plus DEF. So I take 2 vectors. This is the V1 and this is the V2. And I just want to show that I can get to the right-hand side. Okay, so let me ask you a question here, guys. What's the first thing that I'm going to do here? Am I going to add those 2 points together first? Or am I going to apply the transformation first? What happens first? Edgar? The formula for T requires me to have one single vector that I'm plugging into T. Do I have just one vector here at this moment? Not yet, not yet. How can I make it so it's only one vector there? Not this time. Good try. How about we just literally add them together? Yeah, just literally add them together. I'm not gonna do the T yet. I'm just gonna add them together. A plus D, comma, B plus E, comma, C plus F. I'm just gonna make those 2 vectors into a single vector by adding them together. So we do the addition first, okay? Now I have one vector inside of this transformation, and I know how to do T of that. So I'm going to now go ahead and do it. By the way, over here, okay, resist the temptation to write anything else on this side of your paper. Leave it blank. So all of the work is now going to be connected by equal signs on the right-hand side only, and just have white space under that left side, okay? So how do I do this? I can see what my output is supposed to be. There's a 0 in the upper left and lower right corners. What about these other corners? So the top right corner has it says A minus B plus C, but the way I need to interpret that is first slot minus second slot plus third slot. Whatever is in the first slot, that would be A plus D, minus whatever is in the second slot, that'd be minus B minus E, plus whatever is in the third slot, that would be C plus F. Okay. First slot minus second slot plus third slot. Okay. Now in the lower left corner, it's kind of the other way around. I have the negative of the first slot plus the second slot minus the third slot. So the negative of the first slot would be minus A minus D, and then plus the second slot is B plus C, and then minus the third slot, which is minus C minus F. It would look like that. It would look like that. Now, there's a little question about what am I trying to do with, like, how do I know where to go from here? And I will admit that sometimes I get stuck sort of halfway through this, like, well, what am I supposed to be doing? I kind of get my head in a fog or something. It's like, what am I supposed to do? If you sort of lose track of what you're trying to do, don't forget that you can kind of look at where you're headed here. You're trying to get T of the first one plus T of the second one. So I am going to do that for a moment. I'm going to pretend that I'm kind of in a little fuzzy situation. I don't know what to do, but I do know that by the time this is said and done, give yourself some space here though, in between these steps. By the time this is said and done, I want to have T of ABC plus T of DEF. I want to have them separated. See that? And I know what T of ABC is. Let's just work backwards for a second. T of ABC, we have the formula right there. It's 0, and then A minus B plus C, and then minus A plus B minus C, and then 0. I have all of that. And then to that, I'm going to add basically another matrix that's the same structure, but with D, E, and F. So there'll be 0 here and here, And then instead of ABC, I have DEF, so this is D minus E plus F. And down here it would be minus D plus E minus F. So I kind of work backwards. This is where I want to end up at the end of the calculation. So where is that gonna, how am I gonna get to that? Well, I'm gonna get to it from these two matrices. And now I look at these two matrices compared to this one. Compared to that one. Does it seem like if I added these two together, it would be the same as this one? Obviously, the zeros are looking fine. What about the top right corner? I have A minus B plus C, and then I'm gonna add that to D minus E plus F. That's exactly all of this stuff, maybe in a different order. Maybe in a different order. I did really bad here. I need one more space. I'm gonna come over here. I'm gonna insert one more space. So I'm gonna do one more equal sign here, guys. I'm so sorry. I just didn't quite leave myself the right amount of room here. One more in between step where I have a 0 and a 0. And what I'm gonna do is I'm gonna say, look, A plus D minus B minus E plus C plus F. I wanna regroup that as A minus B plus C plus D minus E plus F. All of those 6 terms are the same as these 6 terms, just in a different order. How do I know that that's what I want to do? Well, I want to get all the ABC parts together, don't I? And all of the DEF parts together. So right here, they're all scrambled up. The A and the D are, the A, B, and C are all scrambled up with the D, E, and F. So I'm going to untangle them by just kind of grouping them like so. And then same thing down here, negative A plus B minus C plus negative D minus, sorry, negative D plus E minus F. Something like that. So that step would be nice to include. Now, some of you might be thinking, well, I could have gone straight here to here. I didn't need to write this other matrix down. That's okay. If you didn't write this step down because you could just see it, but yeah, I can see how I want to split these 6 terms into 3 and 3. I'm okay with that. Okay, just don't make such a huge leap that it's like not obvious that that algebra would work. But yeah, you could have skipped that step if you really wanted to. Let's put a little check down here because that checks that T respects addition. Okay, and now I'm going to come over here and I'm going to try to convince you that T also respects scalar multiplication. Let's try this one. And so for this one, I've got to do T of K times ABC. So I'm looking at this formula here, guys. There's a K, it's a scalar. It's scalar multiplying the first vector, which was ABC. Question?
Are we writing this under?
No, we're starting anew.
Okay.
This is now, so we're done with all this. We take a breath and we kind of start over here. Yeah, exactly. So this is T of K times ABC. And according to part B, what we want to do is get this K factored out. What I see students do way too often, though, is they just try to pull the K out right away. The first step, we need to derive that the K comes out. We're not just going to pull it out in front automatically. That's what we're trying to show here. So what's the first thing I probably need to do here? Say again? Yeah, I need to distribute the K inside of those parentheses, KA, KB, KC. In other words, I need to make a single vector that has the K distributed into its components. So KA, KB, KC. All right, now let's transform that. Let's transform that. I got 0 in the upper left corner and lower right corner. What goes in the upper right corner again? The formula tells us that is first input minus the second input plus the third input. So let's do that over here. First input is KA minus the second input, which is KB, plus the third input that is KC. And I'm going to do the same exact thing in the lower left corner, the negative of KA plus KB minus KC, like that. Now, again, if we at some point get stuck we can always go to the bottom and say, what do we want to end up with? What we want to end up with is the K on the outside of the whole thing. But let's see, do you think you have an idea how we could get the K to go out into the front?
Hope we can pull out the case.
We can just factor it out, can't we? We can literally just factor it out. There's a K in every single position of every single slot. I can literally just using matrix algebra, I can just pull it right out of there. So that would leave me with 0 and A minus B plus C, and then minus A plus B minus C, and then 0 again. Just like that. And guys, that is, one more step, that is K times T of ABC. Put another check. K times T of ABC. And again, I just wanna remind you, we're not writing a whole lot on the left side here. Try to have just white space underneath this first step on that side. All right. Is that okay? Does that make a little bit of sense? Let's try another one. Unless there's a question here. Actually, before I try another one, you remember when we were checking subspaces?
Yep.
The main thing we have to do when we check subspaces is closure under addition and closure under scalar multiplication. But there was sort of a first thing that we could do.
Zero check,
Say it again.
zero check.
It's very fast. You remember the zero vector check? If the zero vector check failed, then we got to stop right away and say, no, it was not a subspace. So I'm kind of wondering, wouldn't it be nice if there was something like that here as well, right? Turns out that there is. It turns out that there is. I'm going to state this as a fact, and then I'm going to show you how quickly you can use it. There is a zero vector check for this topic as well, right? So before you worry about seeing whether T respects the vector space operations, you can do this fact first, and I'll just call this the zero vector check as well. And what it says, guys, and I need to get my camera pointing to the right thing here. What this says is that if T is linear, if it's linear, then it must preserve the zero vector. In other words, if you take T of the zero vector, I'm writing this as 0 sub V because remember the vector space V will have a zero vector, and the output of that must be the zero vector of W. It would have to work that way. So this is again useful for showing that something is not linear. Okay, so if this zero vector check fails, if T does not respect the zero vector, you can stop and you can say, okay, that transformation isn't going to be linear, and you don't have to do any more work. You don't have to do all this work that we were just showing. Okay, remember, both of these vector spaces have a zero vector. And what we're saying here is that T has to send the zero vector to the zero vector. It's actually not that hard to prove that, but I think I'll wait to do that until maybe next time. It's very easy to show that a linear transformation is going to preserve that zero vector. But just to give you a quick example, what if I define T from R3 to M2 of R via T of ABC, do the same kind of thing, spit out a 2x2 matrix here. And let's just suppose that what I spit out is 0, A minus B plus C, negative A plus B minus C, and 17. Just making this up as I go. And so it's almost the same exact problem we just did, but now I'm going to ask you, is T linear? You saw it was a fair amount of writing over here. Yeah, I would hate to start doing all of this and then realize 10 minutes later, oh, this isn't working out. it'd be nice to figure out that it's not gonna work faster than that. Well, so let's just kind of using this enlightenment of this zero vector check for the solution here, and I don't need much room. I am just going to check the zero vector right now. So I'm gonna do the zero vector check first. Keeping in mind that if the zero vector check passes, then we have to go on, right? That it's not it doesn't work both ways around. So if the zero vector check passes, then we're back at square one again. And we have to look at the two properties here. Okay, but let's just check it. So what is T of 0, 0, 0? That's my inputting my zero vector. Let's see, what do we get when we plug in 0 for A, 0 for B, and 0 for C? Well, I get 0, 0, and here I get 0. Oh, I get 17. Okay, this is not a big surprise, and that is not the zero vector. So give myself a little more room. That is not the zero vector of W. And so this test that we just did, it fails. The zero vector check fails here. It fails. And so that implies the answer to this question is no, T is not linear. T is actually not linear in this case. All right. So if the zero vector check fails, we can stop. Let's do another example. Oh, by the way, and if, let's say you do check that T is respecting addition and scalar multiplication. If T doesn't respect addition, you think you have to go on and do the scalar multiplication? No, it's just like with subspaces. If the closure under addition fails, it's game over, right? You can just stop immediately. So if anything fails, if at any point anything fails, whether it's the zero vector check or the respecting addition or the scalar multiplication, you can stop. You can just stop just like that. Let's do another good example. So let's do another example here. I'm going to define T to go from the n by n matrices this time. So I'm going to plug in an n by n matrix. And I'm going to output just a single number. So that would be the real numbers. So I'm going to go from Mn of R, and I'm going to map it to the real numbers. And now I'm going to give you the formula via T of, I'm going to plug in just a n by n matrix, which I'm going to write it as capital A. And I have to spit out a number here. And just for fun, let's tie this back into something from a few chapters ago. Let's just output the determinant of A here. So we're going to plug in a matrix, it's a square matrix. We're going to spit out the determinant of that matrix. And the question is T linear? Is it a linear transformation? Okay, so that's the question. So what do you want me to do first? Did you say something? Check the zero vector. Yeah, I would do the zero vector, just exactly what we did a moment ago. Sorry, I can't hear very well. Huh? I can't hear very well. Sorry. So for the solution, I'm going to start with the zero vector check. Might as well. So what is that going to look like? Well, I'm going to take T of the zero vector. The zero vector, by the way, would be the n by n matrix of all zeros. In this vector space, Mn of R, that's your zero vector. Can everybody see my red writing? Okay, so we have to therefore take the determinant of that. So that's the output would be the determinant of that. What is the determinant of the matrix of all zeros? 0. Okay, oh, so it passes. Because that is the 0 for the real numbers. That this time the zero vector check is actually passing. Okay, so we can't quit yet because it passed. So now we have to go on and look at A and B over here. So let's check if T respects addition. So let's see if T respects addition. So how that would look would be T of, A plus B. So notice that I'm, using notation that is appropriate for the vector space that we're in. In the previous example, we used ABC because we were looking at vectors in R3. This problem, I don't have slots, I have an entire n by n matrix, so I'm gonna call it capital A and capital B. And I'm gonna try to see whether this is equal to T of A plus T of B. Now, the formula that you have for T of anything is to just take its determinant. So we're just going to take the determinant of whatever it was that we just plugged in. And we might get to a point like this and be like, I don't know what to do with that. I'm not sure what's supposed to come next. So we can always cheat and go to the bottom. At the bottom, we want to end up eventually, if this property A over there is correct, we should have T of A plus T of B. And sort of taking a step back from that, this would be the determinant of A plus the determinant of B, right? So now my question is, are we okay here? Can I just bridge that gap? Let's see. This is actually a question about chapter 3 again, determinants, properties of determinants. We know that determinants, they were great for transposes. They were great for multiplication, right? Did we have a nice formula for the determinant of A plus B? I think it's in your notes, is listed as a warning that the determinants do not play nice with addition. This is not true. This is not true. Make sure you get that correct in your notes. This is not equal to the determinant of A plus the determinant of B. And so this is a no. T does not respect addition, even though it passed the zero vector check. It's still a no because it's failing to respect addition right here. Okay. Actually, it turns out it will respect it will actually not respect the scalar multiplication either. Both of the properties will fail, but we don't have to worry about that one. This is good enough to show that it doesn't work. If you want, when something fails like this, it's usually a good idea to write a specific example of it down. So like give me specific matrices A and B. It's usually what we would do. But I think I'll leave it at this for now, because you can clearly see that there's a not equals to in the middle of that. And so that is game over right there. That is game over. This is not linear. Maybe that's why that guy didn't like determinants. San Francisco State professor down with determinants. It's like, oh, it's not linear, so we can't do the chapter 6 very well with this topic. I don't know. You have to give that guy a hard time sometime. Well, determinants might not be linear, but there is something very important for this class that is linear that I'm going to share with you right now. And if it wasn't, if this next example didn't work, we wouldn't be here right now. Well, you might be, maybe you're thinking that would be a good thing. Because it turns out that although determinants are not going to respect addition and multiplication, derivatives do. Ooh. Derivatives do. And when we're talking about differential equations, we're taking a lot of derivatives in that theory. And luckily, taking derivatives does respect addition and scalar multiplication. And so a lot of this theory that we're learning right now is going to be helpful for us in the last month of the semester when we go back to the differential equations. So let's write down one more example. This is probably the last one we're going to have time for today, but this is an important one. So I definitely want to get this down. Let's define T. T is going to go, I'm going to use polynomials for this to just be, of course, differential equations isn't just polynomials, but let's just do polynomials for this example. So let's do P3 of R to P2 of R via, okay, now this time T is going to accept a polynomial as an input. So I'm not going to call it capital A, I'm going to call it P of X. That would be a better notation. And I'm going to spit out something on the right-hand side that should be a quadratic polynomial. I'm not gonna take just the derivative of it, I'm gonna make it a little bit more exciting. So I'll use p double prime of x minus 3 times p prime of x. This is the one I wanna use. And it turns out that this one is linear. This one is linear, so we could just say, is t linear? I'm just gonna tell the answer now, in case I forget to do it later. So it is a yes. It is a yes, but let's just see how this would play out. Okay, so the zero vector check, I'm gonna go quickly on this part. Have a huge amount of time, I think I can get this done. So if I plug in the zero polynomial, this is, by the way, when I take t of zero, that's not the number zero. That is the polynomial zero, right? This is, what I mean by this is 0x cubed plus 0x squared plus 0x plus 0. That is the zero vector of P3 of R. But we obviously know what happens when we take a derivative of any constant. Namely, all of these things are just gonna be zero, right? So this is just going to be equal to 0, and I'm comfortable with just checking that one off directly. Okay? Let's check that it respects addition. Okay, let's check that this one respects addition. Again, I'm not gonna use an A and a B. I'm not gonna use A, B, C, and D, E, F. I wanna use notations. And there's more than one right answer here, guys, for what notation you use, but I wanna use something that looks like a polynomial. So I'm gonna use maybe P of X plus Q of X. Okay, this is what I wanna use, something like that. And let's just see what this formula tells me to do. This formula tells me to take two derivatives of whatever you plugged in, right? So I'm just gonna do it like this, guys. I'm gonna write it as P plus Q double prime, and then minus 3 times P plus Q prime. I'm gonna suppress the X just because I don't have a lot of time to keep writing that out all the time. So, guys, if you use f of x and g of x, or if you called them P1 and P2, any of those would be fine, right? This is just my choice. I'm just using P's and Q's, but try to choose something that kind of makes sense. We're gonna keep white space over here. Try not to mess around with that too badly. And then I'm just gonna work on this part. And let's try to think ahead here. I wanna get all of the P stuff together so that that'll be T of P. And then I wanna get all of the Q stuff together, which would be T of Q. So I am just gonna kind of jump ahead and say, look, first of all, I know that derivatives can be distributed like this. So I'm just gonna distribute all those derivatives, P double prime plus Q double prime minus 3 P prime minus 3 Q prime. But then the main thing I wanna do is put all of the P parts together. So the P double prime minus 3 P prime, and then secondly, the Q double prime minus 3 Q prime. Something like that. And guys, that is T of P of X plus T of Q of X. That shows that T respects addition. Is that okay? People following that, or am I going too fast? Oh, thank goodness this is true. I would not have a job if that didn't work. We're like, there would be no 250B. Okay, finally, one last thing. T respects scalar multiplication. I'll do this really quick. This one's always shorter. This doesn't take very long. I just have to take T of, let's say I gotta have K times P of X. I take my scalar K this time. Again, I'm gonna preserve white space over here on the left side. And my goal is to get the K factored out, but I don't want to jump too quickly to that. The first thing I really should be doing is applying this formula for T right now. And what it says is take two derivatives of whatever you plugged in. Well, I plugged in K times P of X. And then subtract 3 times one derivative of whatever you plugged in. And again, I'm just suppressing the X to save time. Do we all feel comfortable that constants can factor out of derivatives? Whenever you take derivatives, you're always pulling constants out, right? Well, I can pull that constant out, that's K times P double prime minus 3 times K times P prime. Let's just pull the K right out of that derivative. And what do you suppose I'm gonna do next? Factor that K all the way out, so the K gets completely factored out. It leaves behind P double prime minus 3P prime. And that, my friends, is K times T of P of X. And so this does respect scalar multiplication as well. T is linear. Thank goodness for that. It means Math 250B is still a great class to have because we can use linear algebra when we're talking about differential equations. And that's kind of the point. Guys, thanks for your attention tonight. If you got any questions, I will be around this evening later on. Otherwise, have a wonderful few days ahead and check in with me on Zoom over the weekend. I'll give you my report. Hopefully it's not. I would be safe first and foremost because I don't want to have you guys have to figure the rest of the semester out on your own.
I just read the textbook.
I don't want you to have to just read the book.
Yeah, that's what I'm talking about.
All right.
The way it's just to keep everything neat, or
Yes.
is there something that we're doing?
No, it's because people often don't write these proofs very carefully. If you start working on both sides of the sign, it becomes much more difficult. In terms of understanding what's going on, so that's the reason for it. Yeah.
Whatever they do.